Hello. Hi, Kalpana. Am I audible?
Yes, sir.
Okay. So maybe we'll get started. Uh, is the screen visible?
No, sir. Screen not
Oh, not
visible.
visible. Okay, okay. Let me share it. Is it visible now? Should I go ahead? Is the screen visible?
Yes, sir.
Yeah.
Start.
Yeah. So we'll start with the GATE 2001 question. This question is very simple. They have given two statements, and we should say if these statements are true or false. Right? Statement one is sum of two singular matrices can be non-singular. Now, question is what is a singular matrix? Right? A singular matrix is a matrix. A is singular if determinant of A equals 0. All right. Now, question is, if you start with two n cross n singular matrices, that is the determinant is 0, can that sum be non-singular? Right. So now to verify the truthfulness of this statement, I just need to construct two matrices. Right. Now let me construct two upper triangular matrices. So let's assume we have these matrices 1, 0, 0, 2. Now we in the last class we saw a property that for an upper triangular matrix, determinant is nothing but product of entries along the leading diagonal. Now we have this A1, this matrix A1 has determinant 0, and similarly let me take one more matrix A2 equals 0, 2, 0, 1. Right. Now this is also upper triangular matrix. This also has determinant equal 0. Right? Because if I multiply 0 and 1, I get determinant as 0. Now, one thing you should notice is when you sum A1 and A2, A1 plus A2, then the leading diagonal entries become all non-zero, right? Now, that is why statement 1 is correct. Is it clear? So, when you sum two upper triangular matrices that have determinant 0, it is possible to construct one more matrix via sum of these upper triangular matrices that has no 0 in the leading diagonal, right? That is why statement 1 is correct. Now, to prove statement 2, in statement 2, what are they saying? Sum of two non-singular matrices can be singular. That is, you start with two matrices whose determinant is non-zero, but when you add them, it becomes 0 all of a sudden, right? Now, that is very, in fact, very easy to verify. Let's take two matrices I, A1 equals I and A2 equals minus I, right? Now, A1 plus A2 will be equal to 0, and thus determinant is 0, 0, right? And that is why it's always possible to construct matrices whose sum is singular when you start from two matrices that are non-singular. That is why for this question, both S1 and S2 are correct. Is there any doubt?
No, sir. No doubt.
Yeah. So now then we'll move on to next question. I think this question is very simple. Can you tell me rank of this matrix? Let's assume this is A. Then rank of A equals
One.
exactly 1. Why? Because it's in a row reduced echelon form already. And in the beginning of the sessions, we saw what is RREF. And if a matrix is in RREF, we can simply read out the rank by counting the number of rows that do not have all zeros. Right? So here, row 1 has non-zero entries, but row 2 has all entries that are 0. Right? And because this is in RREF, you can simply count the number of rows. All right. Mind you, if this matrix is not there in RREF, you cannot count that way. In the sense, let's say we give A equals 1, 1, 2, 2. This you cannot simply say rank of A is 2, right? You can only read the rank by counting number of non-zero rows only when A is in RREF, right? Now, if you are given, let's say, this matrix, first thing what you should do is you should convert this into RREF. For that, what you will do, R2 equals R2 minus 2 times R1. That will give you 1100. Right? Now, this is in RREF, and from this matrix, you will read the rank. So, rank of this matrix and rank of this matrix is both 1. I hope this is clear. Actually, sorry, I'm unwell, so I may be coughing and there may be a lot of inconvenience. I'm sorry about that. Okay, so but nonetheless, is this concept clear? Like you should find out rank only from a row reduced echelon form. Okay, I assume that this is clear. Now let's go to next question. Now in this question, they are asking number of n cross n possible symmetric matrices, and you have one constraint that entries of the symmetric matrix can be either 0 or 1. Right? They are asking us to count the number of such possible symmetric matrices. Right? Now, one thing you should notice is symmetric matrix has a constraint that moment you fix, let's say A is symmetric, the moment you fix entry A of I comma j, then A of j comma I also gets automatically fixed. Right? Now, because you have the structure in symmetric matrix, you have freedom to choose entries only for either upper triangular or lower triangular. Right? Let's assume this is n cross n matrix. Then, once you fix, sorry, once you fix, once you fix leading diagonal and the entries above leading diagonal, then entries of lower triangular matrix is automatically fixed, right? That is why when you're counting, you should count only number of entries in this leading diagonal and number of entries above the diagonal, right? Now, when you start counting, you will start with the upper right corner. You will have one entry, right? Second diagonal, you will have two entries, and you will likewise you will come all the way to n entries, right? So the number of items that you have freedom to fix is 1 plus 2 plus up till n, right? Now you know the sum of n natural numbers formula. What is that? It is n into n plus 1 by 2. So sum of natural numbers starting from 1 is n into n plus 1 by 2. Now because they have given the constraint that each entry in this symmetric matrix is either 0 or 1, then number of possibilities you have is 2 power the number of entries that you can fix. That is 2 power n into n plus 1 by 2. Right? That's why option is C. Is there any doubt in this question? Should I move ahead? Let me know, you can unmute yourself and let me know if you have any questions, right? Otherwise, I'll assume that things are clear and I'll go ahead. Okay. Yeah. Now, let's move on to next question. This is GATE 2004 question. So this question also we have seen in the earlier classes, right? When it comes to matrix multiplication, I told you that it is not commutative, right? The order in which you multiply the matrices is very important. You cannot interchange. Unlike multiplication of integers or real numbers, you cannot simply interchange the order of the matrix multiplication, right? Now, in this question, they have given two things. One, you have four matrices A, B, C, D, right? And further, you are given that each matrix has non-zero determinant. What does that mean? If a matrix A has non-zero determinant, it means that A is invertible, right? Because each of them have non-zero determinant. You have A inverse, B inverse, C inverse, and D inverse. All of them exist, right? Now they are asking the formula for B inverse, right? Now you are given a equation A B C D equals I. Now first thing what I should do is keep B on one side and remaining terms on other side, right? Now to do that, let's see how to obtain that. First, what I will do is to left multiply with A inverse, right? Once I do that, what I'll get BCD equals A inverse I equals A inverse, right? Now what I should do is right multiply with D inverse, right? Then you'll get BC equals A inverse D inverse, right? At last you should right multiply with C inverse. When you do that, you get B equals A inverse D inverse C inverse. Now because you want to take B inverse will be A inverse D inverse C inverse the whole inverse, right? You know the inversion formula that AB the whole inverse equals B inverse A inverse, not A inverse B inverse, right? The order gets reversed. Now when you apply the same formula, you get B inverse equals C D A. Is it okay? Is there any doubt in the question? Okay. So should I go ahead to the next question? Now this is kind of a interesting question, right? Sorry. Uh, so uh, you are given a matrix F that is n cross n, that is symmetry, and you are given a column vector B, right? You are given a column vector B. Now you assume that there are two column vectors u comma v such that u is not equal to v. So u is not equal to v, but you have fu equals b and fv also equal to b, right? Now in the previous class when we discussed solutions to system of linear equations, we saw that a matrix can have either zero solution or one solution or infinitely many solutions. A matrix cannot have more than one but finitely many solutions, right? Now that should give you some hints, right? When the matrix has two solutions u and v, let me change the pen color. When the matrix has two solutions u and v, this automatically should trigger the idea that this matrix has infinitely many solutions. It cannot simply have two solutions, right? And now if you backtrack, if a matrix has infinitely many solutions, we know that the determinant of that matrix should be equal to 0, right? And that is why option A becomes immediately correct. All right. And option B also we just saw. Fx equal to B has infinitely many solutions, right? Because you have because both u and v are valid substitutes for x, right? When you substitute u and v, basically fx equal to v is satisfied, and because a matrix has two solutions, it should have infinitely many solutions, right? Now option C, they are saying there exists x that is non-zero that has fx equal to 0, right? And this also we saw in the previous class when b is 0, when b is 0, when we saw system of linear equations, right? We saw homogeneous system of linear equations. In homogeneous system, basically b will be equal to 0, and when b is equal to 0, you either have only trivial solution or you have I mean when b is 0, if the solution is only one, if you have only one solution, then basically you just have trivial solution, that is x equal to 0. Now, because you know determinant of x is equal to 0, it should have infinitely many solutions, and that is why there are infinitely many x that satisfy fx equal to 0, right? This matrix F does not only admit trivial solution, it admits infinitely many solutions, even in the case when b equals 0, that is even when the system of linear equations is homogeneous. So this also we saw in the previous class, right? Now that is why option C is correct. Now option D, F must have two identical rows. Now this is correct, right? Because in the row reduced echelon form, you definitely need at least, sorry, so the two rows may not be identical, right? Yeah, because you uh, from the design, from the specification of the question, all you need is in the row reduced echelon form, you need at least one row that is all zeros. We don't need a constraint that two rows should be identical to each other. Now this condition is false, right? Now it is not necessary, to obtain infinitely many solution for a matrix F, two rows should be exactly identical. That is not at all required, right? That is why option D is incorrect. So this question they are asking to identify the false statement. Answer is D. D is false. All right. Is there any question? If there is no question, basically we are done with five questions for the day. Ram Sevak, is there any question? And Kyati, was the solutions clear?
Good evening, sir.
Yeah.
Sir, I wanted to know that these classes are held daily.
No, no, it is held weekly, every Friday.
And sir, I cannot see much live classes for computer science
Yeah,
subject.
problem is for computer science, I am the only TA. For other subjects like ECE and all, they have a lot of volunteers. That is why for computer science there are less classes. Yeah, yeah. So if there is no doubt in these five questions, we can break for the day. Or if you have any questions, we'll discuss that. Is there any question that you find difficult?
Thank you, sir.
Yeah. Okay. Yeah. Bye.